You're a miracle. Do you know that? Today we're going to talk about animal development and the miracle of life. The process that animals go through to turn like a sperm cell and an egg cell into a multicellular organism is incredible. No, it's not just incredible, it's unbelievably, transcendentally magnificent, man. Magnificent! And dudes, the thing is, we're all just like tubes.
Dude, no edge.
I know. So animals, they come in all sorts of shapes and sizes and like smartnesses and things. And in our infinite wisdom, humans have come up with a system for classifying animals based on how similar they are to each other. Today we're going to be talking about some differences between animals at the phylum level here, which happen at the earliest stages of development. That's because a bunch of really big decisions are made within a few moments of the sperm fertilizing the egg. And how this early embryonic groundwork is laid makes a big difference when it comes to what kind of amazing multicellular being you're gonna end up being. Or, you know, not so amazing. Hello, sea sponges! Animal phyla range from the very simplest, like sea sponges, to the more complicated. Signs of an animal's complexity include how symmetrical it is, how many organs it has, and how specialized its cells are. A sea sponge, for instance, is a total frickin' mess symmetry-wise, and it doesn't really have any organs to speak of. In fact, if you were to like blenderize a live sea sponge and then leave the sponge smoothie to settle overnight, you'd wake up the next morning to find the surviving cells had found each other and were reforming themselves into a sea sponge again. Try doing that with any other animal. Actually, no. Do not try doing that with any other animal. The point is that most animals are much more complicated than sponges, and an animal's complexity has everything to do with what happens in the first couple hours of its development. And here's a neat rule of thumb: the more complex an animal is, the more it resembles a tube with some different stuff layered around it. And that's when you're like, Hank, what? Okay, so here's the deal. A really important clue indicating that you're dealing with a complex life form is how many layers of tissue it makes in its very early stages of development. Sea sponges make just one, things like jellyfish and corals make two, and all the more complicated animals make three. So the early stages of development are similar for most animals. Remember, sperm cells and egg cells are both gametes, haploid cells that only carry one set of chromosomes. Once the sperm fertilizes the egg, the two haploid cells fuse their information together and form a zygote. One beautiful diploid cell with two sets of chromosomes that contain all of the instructions needed to create a new living thing. Which is, of course, totally far out. Fast forwarding to like an hour and a half after fertilization, the zygote has started dividing and cleaving through mitosis, resulting in 2, 4, 8, 16 cells, until it creates a solid ball of 32 cells. This is actually a morula, or morula, at least according to this guy.
Morula, or morula.
And the morula actually looks a lot like a raspberry or a mulberry, which is what it's named after in Latin. Juicy. Morula pie. Oh God. They're gonna ban us from schools. As more cells are created, the solid wad of cells begins to secrete a fluid that forms a space in the center, resulting in a hollow sphere of cells called a blastula. Okay, so pay attention because here's where we're gonna get down to the real business. Most animals that you just sort of think of off the top of your head have a mouth, right? And by the same token, most of them have an anus. And yeah, you go ahead and get your giggles out now because I'm going to be saying anus a lot in this video. For example, right now, anus. So most animals have a mouth and an anus. Wait for it. Unless you're a sea sponge. Sponges don't have a mouth or an anus. And there are also other animals like your sea anemones, your jellyfish, your corals that have just one hole that serves as both mouth and anus. Aren't you glad we're a little bit more complicated than that? It's worth noting that these animals have radial symmetry. All their junk kind of radiates out from a central point that is their mouth hole / poo hole. And that is a little bit more sophisticated than having no symmetry at all like a sponge, but just barely. I mean, their anus and their mouth are the same thing. But more complex animals, with the notable exception of the echinoderms like starfish and sand dollars, exhibit bilateral symmetry. We have two-sided bodies that look the same on both sides. Something else we have in common is that we have an anus that is, get this, in a different place than our mouth. This separation is pretty key because it means that we as animals are basically built around a tube, a digestive tract, with a mouth at one end and an anus at the other. The process of forming this tract is called gastrulation, and it's kind of a big deal. So when we left our little blastula, it was still just hanging out a little round hollow ball of cells. Gastrulation begins when an indentation starts to form at a single point on the blastula. This place on the blastula that starts to invaginate or fold in on itself is called the blastopore. Now, for animals whose mouth and anus are the same thing, this is where the development stops, which is why they only have one hole for all their business. But in everything else, the invagination continues until the indentation makes its way all the way through and opens on the other side, creating what is essentially a hollow bead made of cells. Now we have a gastrula. Now, two different things can happen at this point, depending on what kind of animal this is going to be. It can either be an animal whose mouth is the orifice that's formed by the blastopore, called a protostome, or one whose anus is the structure that's created by the blastopore, and that's called a deuterostome. So guess which one you are. Write it down. I want to see your guesses. Chordates, that is to say all vertebrates and a couple of our relatives like starfish, are deuterostomes, meaning that we were once just a butthole attached to a little wad of cells. And that includes you. And me. Congratulations! And hopefully you're getting the idea here. The formation of the digestive tract is the first thing that happens in the development of an animal. And it happens to every living thing, whether it's going to be a tardigrade, or a polar bear, or a T-Pain. The miracle of life! Now, so far the little hollow bead of cells is basically 2 layers of tissue thick, an outer layer called the ectoderm, and an inner layer called the endoderm, and these are called your germ layers. For those organisms that stop developing at this point with that classy mouth-anus combo, they only get 2 germ layers. They're called diploblastic, and they were born that way. It's totally okay. But for us more complex animals whose mouths are separate from our anuses, we develop a 3rd layer of tissue, making us triploblasts. Here, the ectoderm is going to end up being the animal's skin and nerves and spinal cord and most of its brain, while the endoderm ends up forming the digestive tract, the esophagus and stomach and colon and stuff. And in addition, some of the cells start breaking off between the endoderm and the ectoderm and form another layer called the mesoderm. These cells will eventually end up as the muscles and the circulatory system and the reproductive systems, and in the case of vertebrates, most of the bones. So what's our embryo looking like now? Awesome. From here, this little guy is going to go on to fulfill his destiny as a ladybug or a walrus or whatever. And now this seems to me like a great time to take a look at a completely disproven theory that biologists hold in the highest contempt, but which is actually a kind of useful way to think about the way that an animal embryo develops into a fully formed animal. Plus, it makes for a great biolography. Back in the mid-1800s, a German zoologist named Ernst Haeckel tried to prove what we now refer to as recapitulation theory. Basically, and this is not basic at all, recapitulation theory states that ontogeny recapitulates phylogeny. In other words, ontogeny, or the growth and development of an embryo, recapitulates or sums up phylogeny, which is the evolutionary history of a species. So this means, for instance, that a human embryo over the course of its development will go through all of the hundreds of millions of years worth of evolutionary steps that it took for a single-celled organism to evolve into a fully tricked-out person. Haeckel was a contemporary of Darwin, and On the Origin of Species made a giant impression on him, especially a section of it that notes how cool it is that all vertebrate embryos look pretty similar to one another regardless of whether they're mammal or bird or reptile. Darwin, however, cautioned that this probably wasn't a very good way of reconstructing the history of evolution. He just thought it meant that the embryological similarities were evidence of common ancestry between species. Well, Haeckel was kind of a spaz, and he definitely heard the first part of Darwin's idea, but not the rest, so Haeckel jumped onto this idea and very quickly wrote a couple of books about how the development of an embryo mirrors the evolutionary development of adults of a species, which is exactly what Darwin said was not happening. Anyway, Haeckel did spend a lot of time looking at embryos and observed that the slits in the neck of a human embryo resembled the gill slits of fish, which he took to mean that we must have at one point had a fish-like ancestor. He drew tons of figures of different animal embryos in different stages of development to prove his theory, and his illustrations of embryos started to make their way into textbooks all over the world. Haeckel is exactly the sort of person who really ticks other scientists off, because real science-loving scientists like like to sit and think about stuff, to find out all the problems with an idea before they start publishing books about it. And here Haeckel was, firing off volume after volume, and before long, all the data he had collected convinced a bunch of other people, including Darwin actually, that he was onto something. But in the end, it turned out that Haeckel was kind of fiddling with his drawings of embryos to make the data fit his recapitulation theory instead of, making the theory to fit the data. But by that time, everybody already knew about the theory, and if there's anything harder than teaching people something, it's unteaching them something. So here we are, almost 150 years later, and we're still talking about the recapitulation theory. But that might have less to do with the stubbornness of a bad idea than it does with the fact that it actually makes a kind of sense when you don't take it literally. At some point in our embryonic development, humans actually do have gill slits like a fish, and tails like a dog or a pig or a jaguar, and webbed fingers and toes like a frog. So while it's not true that every zygote reenacts all of animal evolution, the way that an animal develops does remind us that we are, in fact, related to other chordates. And we start off as just a tube, a mouth at one end, and an anus on the other, which is pretty frickin' amazing. Thank you for watching this episode of Crash Course Biology. If you're confused about any of the anus that we covered today, you can go back and watch that now. And if you have any questions for us, you can leave them down in the comments below or on Facebook or Twitter. Thank you for watching, and we'll see you next time.